Okay, so in this instance, we've got an equation here where we've been effectively asked to balance it, and we've been asked to use only whole numbers in our final balanced equation. Okay, so what am I gonna do to try and figure out what the balanced equation would be? So the first thing I'm gonna do is I'm gonna do an audit, right, of what are the number of atoms of each element on the left hand side, right, on the reactant side of the equation, and what are the number of atoms of each element on the right hand side, so the product side of the equation. And I mean, as you can kind of see from observation, this is a combustion reaction, right? But in any case, let's focus on the actual balancing aspect of this. Okay, so we've got carbon, hydrogen, oxygen, right? So let's look at our left hand side, right? So we've got carbon, hydrogen, oxygen. Similarly, of course, on the right hand side, we've got carbon, hydrogen, and oxygen. And so for this process, I'm simply going to add up the number of atoms, or the I would maybe use the word atoms, or say the occurrence of each element on either side okay, so for carbon we've got 2, right? So C2, so we've got 2 carbon atoms effectively. For hydrogen, you can see we've got 6, right? And for oxygen, we've got O2, right? So we've got 2 oxygen. If we take our attention to the right hand side, for carbon, we've got effectively 1, right? For hydrogen, it only occurs in the H₂O, we've got 2 of those. And for oxygen, this occurs in both of the species that occur that are present on the right hand side. So we've got O2 and we've got O, so that's going to be 2 plus 3, right? So that's not 2 plus 3, 2 plus, I jumped ahead of myself, so it's going to be 2 plus 1, right? So that's going to be 3. Yeah. Okay, so as you can see from the the numbers we've got once we've done this auditing process, none of our elements balance. The carbon's not balanced, the hydrogen's not balanced, the oxygen is not balanced, right? So how am I going to try and make this a bit more balanced? Well, what I'm actually going to do is I'm going to focus first on the carbon, okay? And I'm going to focus first on trying to get the carbon on the right hand side to be the same as the number of carbons on the left hand side, right? So how can we do that? Well, the only species in which carbon occurs on the right hand side is in the CO2, and we can see that we've got effectively half the number of carbons compared to on the left hand side. So I'm going to put a 2 in front of the CO2, and that's going to be the adjustment I'll make to try and get the carbons to be balanced. So if I do that, I'm going to draw out what the new equation I get is going to be. That's effectively going to be C₂H₆ plus O2 produces, and so we put now the 2 as we just discussed. We're going to put 2 CO2 plus H₂O. Okay, now remember we didn't change anything on the left hand side, so when we do our auditing for this next step, we are not going to have any change on the left hand side, so that's going to be quite straightforward. So left hand side for carbon, hydrogen, oxygen, simply going to be the same thing, 2, 6, 2. Now for the right hand side, we did put a 2 in front of the CO2, and that doesn't just affect the number of the carbon. Because we've got oxygen present in that species as well, it's going to affect the oxygen also. Okay, So 2 CO2, so that's gonna it's gonna effectively double the number of carbons, which was our aim, our primary aim anyway. There is no hydrogen present in this particular species, so it doesn't affect the number of hydrogens. It's still going to be 2. And for oxygen, as you can see, oxygen occurs, as we said, in both species. We've got 2 CO2, so that's going to be 4. But then we need to add it to the oxygen here, so that's going to be 5, right? 5. Okay. So now let's look at what we have here. The carbons appear balanced, but the hydrogens are still unbalanced. And the only place where it occurs on the right hand side is in the H₂O. Obviously it occurs in the C₂H₆ on the left hand side. And we have effectively 3 times less hydrogen on the right hand side. Okay, so what am I going to do to try and balance this part out? Well, what I can do is I can put a 3 in front of the H₂O, right? That's the only place where I can really affect the number of hydrogens on the right hand side straightforwardly. And when we do that, well, let's see what we get. So let's add that 3. Then let's audit our equations and see what happens. Okay, so what's that going to give us? It's going to give us C₂H₆ plus O2 produces 2 CO2 plus 3 H₂O. Okay, so let's now quickly audit this. So left hand side, we didn't change anything on the left hand side, so that is going to be the same. It's going to be as CHO, simply going to be 262. And for the right hand side, it is going to change, right? So on the right hand side, CHO. So for carbon, we've put our 2 in front of the carbon, the CO2, but this is basically the same. I mean, we've not changed much there, and carbon doesn't occur in the H₂O, obviously, so that remains the same as it was before, right? So it's going to be a 2 as it was before. However, for H₂O, we've not just affected the number of hydrogens, we've also affected the number of oxygen. So we do need to carefully count that again. So here, of course, 3 times H2 is going to be 6, right? Which was what we were mainly aiming for. But for oxygen, we've got 2 times 2. So we're going to have 4 oxygens from here, and we're going to have 3 times 1 effectively, right? So what does that give us? That's effectively going to be 4 plus 3. So for oxygens, we're actually going to have a 7, okay? We're going to have a 7 here. And as you can see, that has kind of, what we've got here now is that the hydrogens are equal on both sides, the carbons are equal on both sides, but the oxygens are not. And primarily what we've got here is a case where on the right hand side we've got 7, and on the left hand side we've got 2. Now if we were to look at what the multiple is in terms of the difference in oxygens between both sides, we can actually say that the difference is 3.5, okay? 3.5. That is to say that if we were to, another way to represent 3.5 is 7 over 2, right? 7 over 2, right? So 3.5 is actually the difference, it's the multiply between the two. So, and we have actually oxygen on its own on the left hand side, which means we can actually scale up the oxygens without affecting the number of any other element on the left hand side, which is quite convenient. But the actual multiplier to create that in a single step is 3.5. Okay, so that's actually what I'm going to do. So I'm going to add a 3.5 in front of the oxygen that is present on the left hand side. Okay, so let's go ahead with that. So if we do that, we're going to get actually I'm going to use something a bit different. I could just use green. C₂H₆ plus 3.5 O₂ produces 2 CO₂ plus 3 H₂O. Okay, and as you can see, we did not change anything on the right hand side, right? It's the same as the prior equation, so the numbers will be the same, right? So if we just write that out quickly, C₂H₆O, it's going to be the same. It's going to be 2, 6, 7. Now the left hand side is what's going to be different. But remember, the only thing we actually modified was oxygen, right? We modified the O2. So for every other element, it's going to be the same. So for carbon, it's going to be the same. For hydrogen, it's going to be the same. But for oxygen, we're going to have to do the 2, which we had before, as in terms of O2 multiplied by 3.5. which of course is going to give us 7, right? So O is going to be 7. And now we can actually say that this equation is balanced, right? As you can see, on the left hand side we've got 2, 6, 7. On the right hand side we've got 2, 6, 7. But we do need to compare this with what we've been asked to do in our question. And if we do refer to that, what do we find? We find that there's a slight complication in that the question specifies please use only whole numbers when balancing the equation. So the issue we find ourselves with is that 3.5 is not a whole number, obviously. It's you know, got a decimal there. So how are we going to resolve this, right? Well, what we know is that if we had 7 over 2, right? If we multiply this by 2, right? Then the 2's effectively cancel out and we're left with 7, which is a whole number, of course. So we can apply the same principle here, but because it's an equation, whatever we do on the left hand side as far as trying to do like a multiplication of the to keep it balanced anyway, if you want to keep it balanced, whatever we do on the left hand side, we need to do on the right hand side as well. And so what I'm effectively going to do is I'm going to multiply every single species by 2, right? And what is that going to give us in this instance? Well, let's find out. So that's going to be 2 C₂H₆ plus 7 O2, and that produces 4 CO2 plus 6 H₂O, right? Okay, so what we're going to do is we're going to audit this and take a look at, well, is it still balanced? Now, understandably, it is quite clear just from maybe a visual inspection that it is, but we're just going to formalize our thinking in terms of putting it in writing, right? So CHO, right? So what we did is we multiplied all the species by 2. We put a 2 in front of everything. So we multiplied whatever it was originally by 2. So carbon, we've got 4 carbons, right? So it's just multiply by 2. Hydrogen, we've got 2 times H6, which is 12. So which is, as we would expect, it's just multiplying the 6 by 2. For oxygen, we've got 7O2, which is just 7 times 2. We've got 14 effectively, right? And if we now look at the right hand side, right, C₂H₆O. And notice, although I am bearing in mind that all we've done is literally just doubled these values, the reason why I'm still looking at the equation itself is it's more a measure for error checking myself to make sure that I didn't accidentally put a wrong number in the writing whilst thinking of the right number, if that makes sense. So I'm actually checking not just what I think it should be, but what does the equation I've written on the paper, effectively what I've written, what does that actually add up to, right? So that's an important, I would say, error checking step. So I'm actually looking at what's happening here. So anyway, in the case of carbon, we've got 4 times the carbon, right, as you can see. So that's going to be 4. You've got 4 times O2, which is going to give us 8. But we've got 6 times O2 here, right? So we're going to have to do 8 plus 6, right, which is going to give us 14, isn't it? So for oxygen, we've got 14. And for hydrogen, we've got hydrogen occurring in the H2O. So 6 times 2 is going to give us 12. Now, this is as we would expect based on what we were trying to do. We're trying to double everything. But I've just, as I just explained, I've just checked the actual equation I've written to make sure that that actually aligns with what I was trying to do. Okay? Because it can be like, if you're rushing or something, it can be quite easy to accidentally make a mistake. But now, if we look at what the audit has produced, and if we look at the actual equation itself, we can say this is now not only balanced, but we've also used only whole number values to balance it, as the question specifically requested. Okay, so it's 2, 7, 4, 6. Right, so I can just put here 2, 7, 4, 6. Okay, and so this here is our balanced equation. Okay, right.